We're going to start with our next speaker, Sonia Glumich from the Air Force Research Lab. And as she said earlier, she works as the interface to make the support happen for this program with the Griffiths Institute, which is the civilian arm that actually funds this program. And so she works to make that happen. But she also is going to talk about perspectives on cyber. So tell us more about yourself while you're doing that. All ears.
Sure, absolutely.
Okay.
Thank you, Bernie, for the introduction. I appreciate that.
Well, and we've gotten to know her over this last year. Really appreciate her. She's really invested in seeing students going from here into the cyber workforce. So,
Yeah, absolutely. I love programs like this because I am a former scholarship for service student, a cyber core student. I don't know if any of you are in that program, but it's crazy how one program can kind of change the entire trajectory of your life. I never imagined working for the federal government when I was going to college. I never imagined ending up living in New York State. I'm originally from Minnesota. So, New York was never on my radar, but, I just happened to take a course in cybersecurity. It was my last semester of school, and I had to take one more elective, and I took cybersecurity. I thought, well, this will be interesting, and I took the class and heard about the opportunity, and now kind of here I am today, working for the government, just on a completely different trajectory. So it's really exciting for me to be able to work with the Viceroy program and the Viceroy students, because I love being able to provide those kinds of opportunities for other students. So yeah, super happy to be here. Thank you so much for the invitation to speak. So today, the original topic that was proposed to me was DoD perspectives on cyber. But the DoD is a little prickly about people speaking on its behalf. So we tend to, especially when we're going into things like opinions about things, and some of these, I guess, would be my formed opinions after working for the Air Force for the past 17 years. So any opinions I express, findings or conclusions or recommendations, those are my opinions and they're not endorsed by the government. So common disclaimer. So I changed it from DoD perspectives to really, these are kind of my perspectives on cyber after working at the Air Force Research Lab. All right, so yep, I've worked at the Air Force Research Laboratory for 17 years. I love it. Working for the federal government, I think it's kind of like, it's somewhat like working for a university. There is quite a bit of bureaucracy to overcome. I submitted these slides maybe 2 months ago in March. We have to set anytime we do anything to the public, it has to go through a process to be approved for public release. And I just got the approval yesterday at 3 o'clock. So I was sweating it a little bit. I have other slides I could present, but I really wanted to do the ones I had done specifically for this event. So working for the government, there is bureaucracy, but you get to work with so many great people. I'm surrounded by scientists and engineers every day. There are people once in a while. We have some characters that walk around in a white lab coat, and people that are working on quantum computing. We have quantum computers that people are working on. People are working on neuromorphic computing. We have our small unmanned aerial vehicles group. They have a whole airfield. They're flying unmanned aerial vehicles all the time up there doing their counter UAS work. So you really do get to work in a fantastic environment with a lot of people who are engaged and motivated, just really good people in general. Like I said, imagine it's similar working for a university. A lot of people, scientists and engineers, and that care about what they do, just in general, really good people. So I really have enjoyed my time working at the Air Force Research Laboratory. I actually got brought on to the Air Force Research Laboratory to work for our Advanced Course in Engineering Cybersecurity Bootcamp. I was the curriculum director for several years, and that really is focused on offensive and defensive cyber warfare. And that would be a great opportunity for some of these students if you're really interested in cyber operations. They do the whole, the planning and execution cycle. They have a 72-hour long exercise at the end where they have shifts continuously. So it's really hardcore. It's a great opportunity. I love working on the ACE program. Quite frankly, that is why I'm here, because of my experience on the ACE program and why I got hired for this position. So my research interests, I wasn't working on education full time. I'm definitely interested in systems engineering, I've developed some systems, and then also cyber vulnerability assessment. While I was developing systems, I would write a requirement specification or I'd create an architecture document, and I thought, wouldn't it be great if there was a team that I could hand these off to that could, verify that these are in fact good. Are they good requirements? Have I considered all of the security aspects of things? And that eventually kind of led me to join. We had an internal team, a cyber vulnerability assessment team at AFRL that kind of looked at their own products. And we look at requirement specifications, we look at architectures and design, and then finally implementation. So hardware and code review as well. And then of course, cyber education and workforce development. As of 6 months ago, approximately, I became the current Vice Roy Air Force Program Manager. And for me, it's a dream come true to continue working with students. The 2 years prior to this, I worked in a vault, and so in a vault there's very little sunlight. I worked on things I can't talk about, and now to come out into the open and be able to actually talk about what I'm doing out in public is really welcome to me. So now I do have a place to work up at the Griffith Institute with lots of windows, and actually at the Griffith Institute there's an airfield behind it, so you get to see the Apache helicopters come in and land. I mean that's where our eating place is. There you can watch So for those of you that are coming here this summer, you'll be working with them. So great. All right, so a little bit about me. Okay, so I have an agenda here. I want to give this presentation in 3 different parts. I just want to make you aware that there is cyber doctrine out there. If you're interested, anybody can read it. There's both joint doctrine and Air Force cyber doctrine that usually borrow heavily from one another, so they're usually somewhat similar. I wanted to discuss some of the challenges of cyber, particularly on the defensive side of cyber that I've encountered through my years of working in the space. I've worked on the defensive side for my entire career. I haven't worked too much on the offensive side other than kind of in the teaching arena. And then introduce Viceroy Maven, and Jennifer, my colleague, is going to be talking about Maven a little bit more. For those of you who are juniors or below, maybe next summer you would be interested in coming. Maybe if you're not already coming. But I know we have a lot of students from Washington State University. And by the way, I just want to say, Bernie, kudos to your curriculum because most of your computer science students, they have through Calculus 3, some of you have formal methods. And the scientists and engineers at AFRL that are the ones that are looking for students to do their internships with this summer love that. So it was very easy to match your students. So, kudos to Washington State University here. All right. Okay, so cyber doctrine, it is out there. It talks about how the Air Force views cyberspace and how it operates in cyberspace. This is really just an awareness so that you know what's out there. They're both 3-12. We have joint, we have Air Force. The Air Force and the DoD in general is just lousy with strategy documents and doctrine. But they're all out there, and a lot of them are publicly viewable. So if you're kind of curious about how the DoD actually performs cyber operations, it's out there for anyone to think about. So surprisingly. All right, so the cyber doctrine, they kind of see it as these 3 different layers. They look at it as the physical layer, which is the hardware, providing storage, transport, and processing of information. Then you have your logical layer. That would be things like your data, your code, your network processes, your protocol, which is layered on top of that. And then your cyber persona, which is your digital representations of an actor or entity, human or automated machines, or AIs, we're all talking about these days. So that is that layer. And they look at them as distinct yet interrelated. So that's from joint doctrine. All right, and they divide the actions in cyberspace into 3 different types of missions. One is offensive cyberation. So if you're here, people talk about OPO or OCO. These are missions intended to project power. So this is all the fun offensive stuff that people do. There is the defensive cyber operations, DECO or DCO, and these are missions to preserve our capabilities, to make sure that we have the freedom to do what we need to do in order to accomplish our missions, while denying adversaries the same thing. And so we're looking at defeating those threats against our infrastructure. This is both protective things that you do at the very beginning before you ever get into a battle, investigative and response actions that occur after as well, in addition to everything in between. And then they also have a separate thing, which is DOTN operations. And really, that's kind of your system administration functions. And so they split that out as kind of a separate area, although certainly that definitely contributes to defensive cyber operations, right? And offensive cyber operations too, because if you don't defend your systems, you can't, and they're not operating properly, you're not going to be able to conduct those other cyber operations. And then I like to add another category in here, defensive cyber operations, where really doctrine focuses on things that happen after you already have your systems in place. So when you're actually conducting your operations in real time, when you're responding to threats. But really, there's not as much of an emphasis on what you do before you get into battle when you're actually designing and developing your systems. So we also address cyber assurance. And so these are the processes that you put into place, before you even deploy the system. So what can you do to tip the odds in your favor before you go into battle? Because on the defensive side, you do have the advantage that you get to build your own chessboard, so to speak, right? So, eventually you're going to be playing a game on that chessboard, but you get to build a chessboard in all pieces. So, you can build your own environment to your liking. Unfortunately, that is a really difficult thing to do, right? Otherwise we could do everything perfectly. All right, so DOTN, there are some unique challenges having to do with DOTN. It covers, a wide variety of things. So, in the government, there is a trend towards moving towards everything is leased, going towards commercial off-the-shelf types of solutions. And so these are things that we really don't control the development process of. It's impossible to know exactly how things have been developed. It's impossible to review every single line of code. So that is a challenge. However, there are financial and cost savings, right? And then there are huge gains in functionality when you can tap the whole COTS market as opposed to developing everything yourself. This includes both network systems and standalone systems. I worked in a vault. A lot of those systems are standalone. They'll never connect to any network. Hardware, software, and data. All of our different classified and unclassified networks. So definitely government systems. NIPRNet is our unclassified network. CyPRNet is up to secret level. JWIX is up to TS, and then there are others that go beyond that as well. This includes not only just traditional enterprise IT type systems like servers, but we have to worry about industrial control systems. You have no power, you have no offensive and defensive capabilities, right? And you probably have no mission, or it's going to be very difficult to achieve. We have DoD-owned smartphones that people have. When they talk about platform information technology, they call those PIT systems. Those are actually the weapon systems, because again, we don't just have servers, we have aircraft to defend. We have cyber-enabled munitions, which have computers on them, bombs and missiles. So we have all sorts of interesting weapon systems that we need to consider from a defensive viewpoint. All right, and then these days, it's been a real kind of hot topic of discussion around AFRL is wearables. AFRL, the tagline is that we are one lab supporting two different services. So we're not only supposed to support Air Force, we're also supporting Space Force. Well, Space Force is looking at doing something new, where right now, if you're in the military, you have physical training, right? You have PT. And so you have tests you have to do, you have, you get together, you do the exercise. Well, they say, can we replace that with a smartwatch? And then just monitor it that way. And so they came to AFRL and we say, well, what goes on with that data? Who can see that data? Can you track that data? There was an incident not too long ago where in the Middle East, when the soldiers are over there with their smart devices, it's very easy to see where the bases are that you're not supposed to know that they're there. But because there's so many smart devices in that area, well, the native population doesn't use those smart devices. And so that data was publicly available. And so you can track different things. So there are definitely concerns when you're talking about, putting a smart device on, a person. Even things like keystrokes. There's research out there, and you determine keystrokes from, or can you get some type of automated system that can figure out what people are typing if they're wearing these devices. So there's all sorts of things that we hear where we're like, well, wait a minute, have you thought of these things? And really, when we're doing, cyber vulnerability assessment, our goal is not to tell them what to do, but to make sure that they are informed of the risks. So you know the true risks of using this device. All right, so cyber doctrine, they also kind of divide into the blue, the red, and the gray. It's kind of, if you guys are in cyber competitions, they'll usually use, blue team, red team. Blue is the defensive, when we talk about blue space, that's the areas in cyberspace that are protected by the US. And red space is portions owned by the adversary, and then gray space is everything else. And so over the past few years, there's definitely been interest in, how do you leverage gray space? What is the right way to leverage gray space in the event of some type of a conflict? Right now the DoD uses a lot of commercial clouds, right? And so it's not really owned by us, but it's depended upon by us. So it's gray space, it's blue space, I guess it depends on your perspective. So it's a little messy. All right. So they also talk about tested cyberspace, where D4M is the new term. It used to be D5 effects. So, you see that on a lot of competitions. You get access to a system and you're like, ooh, well, what do I do now? Well, you do D4M effects. So you might try to deny access to something. You might try to degrade a capability. You might want to be a little more subtle, right? You might not want to outright deny things. You want to cause confusion. So you just degrade. It's a little bit slower. But they don't know that, for sure that you've actually done anything. You might try to disrupt, manipulate, or out destroy. And so, just the systems must be developed considering the contested space. I think this message is out there pretty well now. Everybody knows, we operate in a contested space, but that wasn't true, as much when I started. It was kind of funny, when I started working for AFRL, we couldn't even really talk about the fact that we did anything on the offensive side. That's how taboo it was. You could talk all about bombs, but boy, you can't talk about offensive cyber warfare at all. So, things have gotten a little bit more relaxed in terms of talking about offensive cyber warfare, but, just 17 years ago, they didn't really want to admit that we were working in the space, which is funny, or, they tried to keep it mum. All right, they also talk about key terrain in cyberspace, so analogous to a kill in conventional warfare. So these are going to be, a lot of times in, military speak, they talk about centers of gravity. And so these are the things that are really high value assets that you want to take and maintain. These days, I would say, a great center of gravity would be, cyber defense solutions. So something like an intrusion detection system or a firewall, because if you control those types of systems, network monitoring, if you control those systems, then you control basically all systems, or you'll have access to all systems. And so, that would be an example of key terrain in cyberspace. But unlike, conventional warfare, terrain changes are far more rapidly. Things are constantly changing. Software is being upgraded. Hardware is being changed. So these might be things like a router, an intrusion detection prevention system, a firewall, command and control system. And then again, we run into that problem where sometimes this key terrain is not owned by the Department of Defense. And so, you only have so much control over that. All right, so some of the cyber operations challenges that they talk about in cyber doctrine is they definitely talk about costs. We have these systems which, maybe we go to a contractor for it, and it was developed by, another set of developers that subcontract out to other developers that was manufactured, in places all over the world. And it's very hard to know where all the components are. So that is a real problem with supply chain and then foreign ownership and control of systems. And then attribution is another really big challenge. People want to preserve privacy in cyberspace, but then it makes it very hard to attribute things when people do something they shouldn't be doing, right? Or when our adversaries do things. So knowing how to do it, knowing who did it is a step in deterrence. You can't really deter an adversary if you can't prove that they did something, right? So how can you say you did this and they say, no, we didn't, and prove it, and you can't. So it is difficult because there are some methods out there for anonymity and it's methods of deterrence. All right, so network and infrastructure vulnerabilities. So our currently favored measures for networks, you'll see a lot of talk about firewalls, intrusion detection systems, intrusion detection systems, and training and, our cyber awareness, challenge training that we have. which is, it's funny, we were talking about that earlier. It's the same thing for the DoD, our cyber awareness challenge. It's hokey and, really, it did something, I guess, but, all right. We also have infrastructure, you have errors, you have accidents, natural disasters, purposeful attacks. All these things are going to be challenges, especially these days with natural disasters, as things start to change, climate change, the DoD is very concerned about that. They've put out papers on that topic as well, as to how that can potentially threaten our military readiness. Okay, so the problem with cyber, this is a really old anonymous internet joke, but it's so true. We have systems in the DoD that are really old, and no one really wants to touch them or change them because they don't know what will happen if they do. There's all these cascading effects that will occur. If you change something, other things might rely on it. And unless you understand the system as a whole, you don't know exactly what you're doing when you're changing something. So again, you have a bug, you fix it, you might introduce new problems. And so when you're dealing with legacy systems, this is definitely, a problem. All right. So yeah, why don't people just build, configure, and use systems correctly in the first place? Are people just uneducated? Are they lazy? Are they incompetent? It's all of us. It's the people who create the stuff. It's the people who use the stuff. It's the admin and stuff. Is everybody just, sleeping behind the wheel? They just don't want to do their job. So why not create your cyber systems? And for people who don't work in cyber, I think this is, kind of hard to understand. It's like, well, what's the problem? Why don't you just fix the problem? It should be easy. And then kind of what constitutes the root cause of these vulnerabilities? So why is it this way? Why is it so hard? All right, so is it the ill-trained users? So I usually have like the old memes up here, but I can't do that because when you go through PA approval, you have to prove it, where it came from and everything. But, is it incompetent system administrators? Is it these ignorant system owners that are just unreasonable, constantly changing what they want and, making developers' lives hell? Is it, uncaring system developers and testers? They're like, hey, I did my part, I'm going to throw it over to testing, it's their problem now, haha. That really isn't what it is at all. It could be a little bit of that, but that is not the core problem of why we're at where we're at. So, is it these users that forget or ignore training? Is it customers that change what they want? They want too much too fast or refuse to pay security costs? Is it architects that create these vulnerable architectures and designs for developers that write buggy code? Or is it these operators and administrators that just ignore the training, they just don't care, configure systems in insecure states? There seems to be like a whole lot of blame going around, right? But maybe they're all a little bit true in certain cases, but overall, that is not our problem. Our problem is high complexity, right? These systems are complex. You can be the most dedicated person, and you're not going to be able to understand 40 million lines of code, right? You're not going to be able to understand all the different implications when you have a huge operating system, right? Like Windows. It is impossible. It is too complex for the human mind to really, it doesn't matter if it's the smartest person in the world and most dedicated. So we have systems with hundreds or thousands of subcomponents, millions of lines of code, and it's too complex for the smartest humans to secure. It's just, and then you have systems of systems and how they work together and emergent behavior and trying to secure that. It's complexity. And, this is not a secret if you work in security. Ferguson and Bruce Schneier, they're the ones that, called it out many years ago. Complexity is the worst enemy of security, and it always comes in the form of features or options. As somebody who is new to the DoD coming in, I'm like, well, we just need to make, simpler systems. We need to make sure that they do things the right way. Well, that's really naive. That's just not the way the world works. People want features. They want things that work. They don't, quite frankly, they're willing to take on the risk to have all these things, and they're willing to sacrifice security to get it. They just are. And, our problem over time tends to get worse. That's the happy news on the cyber defense side. Because systems are not going to get less complex. They're only going to get more complex, right? As we continue to build things. Now we have AI/ML, and we have these systems where nobody really knows why they make the decisions they make. And so there's a whole new field of research, that's called like understandable or explainable AI, where we can say, well, why is it making these decisions? And how do we know they're the right decisions? So the trend is it's just going to get more complex. We're going to want more features. And so it's harder than ever for the cyber defenders. Things are more connected, right? Cyber defense is an interesting, field to work in. And the problem is only getting worse. So on the offensive side, that's great news for them, all right? More vulnerabilities, the more complex the system is, the more vulnerabilities it's going to have. So they'll be in business for a long time. All right. So this is, Air Force doctrine is kind of caught up with the times on this. They even acknowledge it in it, but I was surprised to find it, because of cyberspace's complexity, they simply call it out. Global superiority is not achievable. In some cases, even localized superiority may be impractical. And so we are supposed to expect that we have these contested domains, that things might not work, that we're going to be attacked. And so I was surprised by that. Some years ago, we have different CTCs, which are kind of these big groups at AFRL, and I'm in the cyber group. Well, there's another group called AC2. And when they came up with their strategy, they talked about harnessing the power of complexity and making complexity work for us. And I was just like, wow, that is just the exact opposite of what we want to do, in cyber defense, at least. Complexity is our enemy. All right. So, when we're talking about vulnerabilities, they can be introduced at any stage of the system development life cycle. So it can be in requirements. You might be missing a requirement that you need. Requirements are often ambiguous. So by the time it gets to the people implementing the system, they don't know what they meant, and maybe they implemented in a way that they weren't supposed to, or wasn't they weren't intended. They're non-atomic, which means a good, well-written requirement only addresses one thing and one thing only. They might be untestable. So you'll see requirements like the system shall be secure. Well, I mean, that's not measurable. It's not quantifiable. It's not testable. And architecture and design. So, there are specific things you can do in order to minimize vulnerabilities after implementation. So a good example of that is, separating some of your sensitive operations from your less sensitive operations. So separate your sensor data, which an adversary can easily manipulate, from your command and control data on a UAS. Implementation, that would be the code level issues. So like when you take in your input, are you doing verification that input is in a format that it needs to be in? And then deployment operation, configuration issues, where your user and admins come into play all the way down here. Configuration issues, misconfigured, for example, to enable anonymous access to. So when we're talking about cyber defense in particular, there are certain paradigms that we think about in terms of ways to solve the big problem, right? So the detect paradigm is where you say, well, we have these trusted security systems. They're going to monitor these untrusted other systems for malicious logic and behavior during operations. So that would be your intrusion detection systems, your firewalls, your network monitors, things like that. So that's one paradigm. They say, we're going to watch and we're going to wait for something to happen. We're going to detect it and we're going to remediate. That is opposed to the prevent paradigm. There's a couple different approaches to that. One is to design and build trusted mission systems right in the first place. So you're going to design out the vulnerabilities in the first place. So you never have to get to the point where you detect an attack. That's the idealized world, right? So that the malicious logic doesn't get on the mission systems in the first place. Another approach to that is that you set up your architecture and design to enable leveraging untrusted components. So in number one, you're saying we're going to secure everything. Everything is going to be perfect. We're going to make sure that it works exactly as intended. There are no vulnerabilities. Number two approach is like, there's going to be some untrusted components we have to leverage, but we still have to come up with a way to accomplish our mission, even though we're going to assume some of these components are untrusted, which is our problem. Okay, so kind of our current approach in the DoD is we are securing these highly complex and vulnerable systems by adding more complexity and vulnerabilities to them, right? So you take a highly complex system, let's say it's a server, and then you add another highly complex system, an intrusion detection system to it, and that has its own vulnerabilities to it. So that's kind of the way we're doing it today. So these security systems introduce additional vulnerabilities. Unfortunately, they're developed in the same manner as the systems they attempt to protect. So, I mean, that's a good question. If somebody's trying to sell you a security appliance, you say, well, why should I trust that this system is any more secure than the system it's trying to protect? I mean, who's watching the watcher then, right? I mean, why do we assume that just because it's designed for a security purpose, that it's secure? Because they're not developing it any different, unless they're very careful with formal methods and, doing things, the old hard way, right? With formal methods. All right. And then a lot of times there's instances where these detection-based security systems introduce a single point of failure. So they are very juicy target of attack for attackers. We've seen that with recent attacks that go after some of these defensive systems. And then, we still are at the point where this detect approach fails to detect novel events. So you're constantly playing catch up, right? These detect systems have to know about, previous threats. They have to have already seen them so that they can detect them again. Now, there's work with AI/ML. There's been promises that yes, we'll be able to detect zero-day attacks, but I haven't seen it yet. So we'll see if it can generalize enough to be able to detect novel threats. So we'll see. But one paper estimated that the time from when the system is infected to when it's detected is 300 days. And so for on average, 300 days goes by before you detect it. And that's just too slow, right? So the detection approach isn't working that well. I mean, but really there aren't that many good solutions, right? All right, so this is kind of a view of this. We tend to want to assume that this and this are perfect and they are trustworthy and that they will do their job as intended just because they're intended for security. But again, they're highly complex. There's just complexity they're trying to defend, and so they're just vulnerable unless they really take some measures when they're developing these systems so that they're secure. And from what I've seen, I think they do similar software development practices. Okay, so detect. And the problem too with the detect-based solutions, they tend to friendly fire our own systems, right? Because we have all these systems on our government systems. It takes, sometimes I will sit there, I will be on my phone because it takes 15 minutes for my computer to, come up. And that's because we have so many different defensive solutions on them. That they use, there's high CPU, memory, battery usage, impacts functionality, and the number of signatures continue to grow. And then, adversaries, they test all their malware against these detection systems. They have access to them, so they run it through, right? They say, well, I'm going to test my malware against all these and make sure it isn't detected. And then I'll put it up there, right? So, they can make sure that it's not going to be detected. And that will include any AI-based detection system. If it's widely deployed, adversaries will get their hands on them. They're going to test their malware against it. So, but I am looking forward to any results in this space. I would love to see some proof that it actually would, detect zero-day attacks. So, and this is also a problem in the military because we don't have a big database of signatures for a cyber-enabled, JDAM, which is a munition. We don't have signatures specific to that system because they're not widely out there. And so that's a bit of an issue when, putting these systems, people want to put, these detection systems on weapon systems. And, you say, well, where are you going to get the signatures, right? I don't know. All right. So prevent approach number one is where you look at the core function of what your system needs to do, and not what would be nice to have. And you strip it down to the absolute essentials. I have been on different efforts. Like for example, I worked on an effort where we developed a secure memory loader verifier for the F-16. That is something which loads the operational flight program onto an F-16. And we did a prototype of that where was basically a PTA design that had no operating system. Because right there, you eliminate the operating system, you're eliminating a whole bunch of vulnerabilities. We have enough computing power now that we can do single purpose systems. And we did go through the whole, process of doing formal modeling. We used Hall theorem prover, if you guys are familiar with that, and developed a very simple, system. But, the problem is it's very hard to kind of penetrate that market. It was an interesting experience. So, we kind of know that we could do these things, but there's not that much of an appetite for this. But, this would be one approach. And then that's where you engineer confidentiality, integrity, availability, authentication, authorization, et cetera, from the start. So right away, when you're defining your requirements, you're thinking security. You can red team the specifications, those requirements, the architecture and the design. So we call that an early cycle cyber vulnerability assessment, where you insert yourself very early in the systems development lifecycle process. You don't wait until it's already implemented, because at that point, the system owners, they don't really want to know the bad news that there's vulnerabilities, because it will be very costly to go back, or even impossible to go back and eliminate those vulnerabilities. So the idea is you get in at the very beginning. And there has been a movement in the Air Force towards doing earlier testing so that they can insert themselves again earlier in the system development lifecycle. Otherwise, things just won't get fixed. It's too expensive. All right. Leverage formal methods. So specify your system mathematically. Write proofs, find state machines, translate those into implementation, and then in the end, you verify the implementation satisfies the specification. All sounds great, right? All right, so the idea is that you have this mathematically verified system that only does what it needs to do. The question is, really, can this be done? I really like, back in the 90s when they were developing the space shuttle flight control software, which had about 40,000 lines of code, they were really successful in developing bug-free software. I think they only found like one bug in this software, but it took a whole entire building of people to create this 40,000 lines of code. And it was a really intensive process. And it was kind of funny because they said the types of developers that they looked for were like middle-aged people, because it wasn't just, some young person that knows a lot and, just like coding like crazy. And, it was middle-aged people that were going through this real methodical, kind of boring process of testing and going back and forth between the developers and the testers in a very kind of boring process. But in the end, they did produce something that was, practically bug-free. So it is possible, but it's extremely expensive and takes a lot of people. All right. Well, but there are some problems with this approach. Formal methods, tools, they have some limitations. They can only handle so much complexity themselves. Some systems are too complex to do this. It would just take way too much time. But, there is broken automated tools. So for example, Windows 10 OS has about 50 million lines of code. So it's going to have, hundreds of vulnerabilities to thousands of vulnerabilities. So there really isn't too much of an appetite for this approach. Depending on who is in leadership, some of them don't want to hear anything about formal methods. They've been around for a long time. It's slow, it costs a lot of money, and then it reduces functionality. And, but there's some automation tools that can improve. So, there's still work in this space, but there are limitations. And then, but again, our technology adoption trends, we're moving away from GOTS, where we can do all of these types of things. We're moving to COTS, right, where we're just buying stuff off the shelf. So this approach would not work in that case. All right, we're moving towards leveraging these untrusted commercial assets, cloud servers. And so if we don't specify, we don't architect, we don't design and build these systems ourselves, then you need another paradigm. And so, the question is, how can organizations safely leverage untrusted commercial assets for storing and sharing data? All right. So, we at the lab, we have a couple different ideas of potential ways you could do this. One thing is for secure storage is our layer 8 architecture. So this is where we want to leverage an untrusted cloud asset, but we don't want anybody on that cloud to be able to see or change our information. And so what that means is that you take your data, you fragment it into bits, you encrypt those bits, you digitally sign them, and then you store them up in the cloud. And then they're only ever decrypted and verified on your host computer. So that's one way you can leverage untrusted assets. We don't care, you can have access to our encrypted fragments, especially for things where a lot of times we have missions where the data is only good for so long. So who cares if they get it, as long as they don't get it within, a week. So this might be a good solution for something like that. But, there is still limitation of this. you have to trust your client, right? Because if somebody compromises that client, then they'll get access to all that data. They'll be able to pull it all down and reconstruct it. So, we had some different implementation ideas. Again, you could do that in an FPGA, single purpose device. You could do it on an external device that has hardware encryption. So, there are potential things that you can do to kind of raise the barrier for an attack. So that's one idea. But we do have a newer effort, which is Rescue Cloud, and they're actually looking at a much harder problem because they're saying not only how can we leverage the cloud for storage, can we leverage it for computation as well? Has anybody heard of homomorphic encryption? So it's pretty cool. It's like you can send encrypted inputs to the cloud. You can have the cloud do a computation. You can get an encrypted output back, but you can get your answer that way. So, there's a lot of math behind it, but homomorphic encryption is kind of a cool idea. Again, that's still in the earlier stages of, before we can actually use it for something useful, but, there are ideas in that space. All right. So kind of some final thoughts on this, again, complexity is the worst enemy of security. It always comes in the form of features or options. The rising security complexity is outpacing advances in security. You never know, there could be a breakthrough. One thing I like to think about is, maybe the human brain can't get its, we can't get our minds around 50 million lines of code, but maybe AI could, right? Maybe we use that as a tool to design and develop systems. And so there's potential there. So there are solutions, but many of them are unpalatable or unworkable. And so, and then, we always get this argument formal modeling is too difficult to do on highly complex systems. But the counter argument when we're talking about, critical systems where lives are depending on them, if it's too complex to formally model, we might not want to rely on it for the most critical operations. So, it may be that we want to identify particular single purpose systems where we employ the prevent approach. We wouldn't want to do that for everything, but maybe for some of our crown jewels that we want to make sure that they're going to be there for us. Like nuclear command and control, for example, you might want to move towards that end of the paradigm spectrum. And so additional measures, disaggregation or redundancy up in the cloud, homomorphic encryption to overcome lack of trust are currently being researched. So, a lot of times when you hear people that are blaming the user, that is just a real easy thing to do, right? There is a whole reason why we have insecure systems, and it's not just somebody writing down their password. Quite frankly, we should be designing systems where people don't need to remember a password in the first place, because people are going to forget their password. People are people. They're not going to change, well, at least until we get a brain chip, right? All right. So that's kind of my talk on, why is cyber a problem? Why is cyber defense so difficult? And, I did want to put a little plug in here for the basic place where I made the summer internship. I'm super excited to be working with the interns this summer and get to do a little teaching and working with them. I'm kind of the curriculum developer for that as well. So actually, I think our number is closer. We're going to have 50 interns coming this summer and 5 GAs. It's going to run for 8 weeks this summer. And we're really focused on Air Force and Space Force missions. We're going to be doing a cyber vulnerability assessment of a satellite system. You guys, people that are coming, you are going to be doing research projects 3 days a week with an AFRL mentor. We're going to have you write an IEEE style paper so that you're, if you haven't written a research paper, you'll be prepared to do that in the future. So you'll have a little bit of experience writing kind of a military format, which is a Blue Book report, and also kind of on the research side, an IEEE paper, and then also hands-on cyber EMS exercises. So we'll be doing some offensive, defensive operations exercises, as well as just some introductory work with software-defined radios, which I think will be fun. Right. Okay, and I think I'm going to leave the rest of that to Jennifer, other than I think we'll take a peek at the schedule. But for those of you who are coming on Mondays, we're going to be having lectures with a subject matter expert on mission systems, whether it's satellite systems, cyber-enabled munitions, data systems, UAVs, and then on Tuesday through Thursday, I'll be working on your research projects, and then Friday Fun Day, we'll be doing more of the hands-on types of things, but I'm really excited for the summer. I think we're going to have a great time. And, for those of you who haven't applied yet or are on the younger side of things, please do consider applying for 2024. And you'll be hearing about that in the fall. So I hope you will all consider it. All right. And Jennifer will be talking more in depth on the internship as well tomorrow. All right. Does anyone have any questions? So again, perspectives on cyber, not DoD, but kind of my perspectives from working in the field. Well, thank you so much. I appreciate the chance to talk to you all today.
All right, thank you very much.